Yes, I will try to come up with a perfectly cromulent explanation for hot Jupiter radii. So yeah, we've heard a lot of amazing detail about what we know about the atmospheres of hot Jupiters with incredibly detailed spectra and then studies with GCMs of the very detailed dynamics on their surface. But one of the things that I think makes hot Jupiter such a very interesting class of planets and of astrophysical objects in general is that their surface dynamics affects their global evolution over gigayear timescales and affects, basic physical properties like their radii at the tens of percent level. So this certainly makes them unique among planets, I believe. And yeah, quite fascinating overall. So I'm going to describe this problem in general, including some work I'm doing with Tad here, who we've seen is quite an expert in hot Jupiters from all the talks today. So I'll start with a little background, right? And what makes cold Jupiters different from hot Jupiters is that colder Jupiters are objects that are more or less fully convective up to their photospheres. But hot Jupiters, because of the intense irradiation they receive from the outside, it forces the outer layers that heat is sort of redistributed from winds, and so it forces the outer layers into a temperature distribution that's more isothermal, that's incapable of driving convection. And has so there's a much thicker radiative layer surrounding these hot Jupiters. Of course, even that thickness is exaggerated a bit in this cartoon. And so one of the things to keep in mind is that at least in the standard cooling models, the size of a hot Jupiter is the issue we're dealing with, is primarily controlled by the entropy of this inner convective zone. The other factor that's important is the mass of a solid core, or the heavy element composition. Now, if you're trying to explain how things can get so big, the best case you can do is assume that you have a small core, because the more heavy elements you add, that just makes your problem even harder. And so for the most part, that's what we're going to be doing here. And so one of the basic issues that's well known is that the effect of this radiative layer is sort of like a blanket that helps to prevent the hot Jupiter from cooling over time and helps to keep it large. And so that's one of the key issues then, is how can you make this radiative zone thicker, or how can you keep it thick over time? So again, the issue here is, why are hot Jupiters so large? And so what I need to explain is, what do we mean by them being too big? Like, what is our expectation, and why is reality different from our expectations? I'll go over some of the basic mechanisms. We heard about many of these from Kristen already, so hopefully I can go through that relatively quickly and then get to the recent work with Tad in sort of quantifying what are the actual heating requirements that we have, sort of independent of mechanism. So here's a plot from Eric Lopez. Hopefully I'm not stealing from his, no, he's not talking about this today. He'll be talking about some of these issues, I think, later in the conference, where this sort of shows the key issue, that the radius of giant exoplanets, with their masses denoted here in the color bar, correlates very strongly with the flux they receive. The flux here is relative to the flux that Earth receives, would be 1 in these units. And we see here this tremendously strong correlation, that the more intensely irradiated a planet is, the closer it is to its host star, the larger its radius is. And so, but maybe this isn't surprising, right? Hotter things maybe should be bigger. And so the reason this is a problem is that if you run a sort of standard radiative convective equilibrium cooling model and include the irradiation from the outside, that's simply not enough. So here we have another representation of basically the same data of radius versus mass. And now here the color is indicating the sort of equilibrium temperature, if it was just in thermal equilibrium with the radiation it's receiving. And so you indeed see again that the hotter objects are bigger. But what we see here is that when you do a standard radiative equilibrium model, that the predicted radii are indeed larger than Jupiter, but they're only larger than Jupiter of order 1.1 to 1.2 Jupiter radii. that the irradiation is simply not enough to explain why so many objects are 1.4 Jupiter radii and above. So something else is needed, and this is even, these models from Courtney are, again, taking this optimistic assumption that there's no core, optimistic in terms of explaining why they're so big. And so again, just to sort of show the time-dependent nature of this problem and sort of how you can solve it, right, again, the issue is that these standard radiative equilibrium models, the Jupiter can start very big and inflated, and then as it cools over 10, 100, and a gig a year, it eventually contracts to small sizes. And so the irradiation of one of the most famous transiting exoplanets, HD 209458, its radiative equilibrium predicted size is only a bit bigger than Jupiter, but its actual size is much bigger. And the way to make it much bigger is to add heat not just to the surface of it from irradiation, but to add some heat deeper into the interior. And so this was shown very early on by Guillot and Schoeman, that adding heat at various levels below the photosphere in a hot Jupiter could explain these radii. And so indeed, in terms of the mechanisms for how to inflate the hot Jupiters, there's basically only two ideas that's sort of analogous to cooking. You can inflate it either by adding the amount of heat, or you can get a better lid for your hot Jupiter and prevent that heat from escaping. And so again, we think because of this flux dependence that probably the better lid is not the full explanation, because it's not clear why you would get a better lid just from increasing the stellar radiation. But those classes of models are based on the idea that the opacities are somehow different from what we expect, or that convection somehow works differently from what we expect with some sort of layered convection. The ideas of adding heat, one of the original ideas from Peter Bodenheimer here in Santa Cruz, and variations of those ideas have been worked on by Phil Aris and Aristotle Socrates, that there's some form of tidal forcing, which is sort of flexes the planet, adds heat to it. This is, this is not what we'll be talking about here, but this is something that would require an eccentricity on the planet, which we maybe expect to damp over time, or else it would require a special form of thermal tidal forcing. I'm going to focus on these wind-based mechanisms. So again, the original explanation of Schoeman and Guillot was based on this wind circulation depositing energy in the atmosphere. And then there's also the ohmic dissipation idea that we heard a bit about from Kristen. And there's an idea, I'll be mentioning something that I worked on with Jonathan Mitchell, of another aspect of these winds and how they drive turbulence. So let me now just say a little bit more about each of those. Again, the classic idea here is that because you have strong heating on the day side, that winds blow from day to night, and those winds will penetrate deeper in the planet than the starlight does. And so when those winds dissipate and deposit their energy, they can help explain this radius inflation problem. The issue, as we've already discussed a significant amount, is that how deep these winds are is quite uncertain. The GCMs say they're relatively shallow, but we've had extensive discussions that maybe that's the GCMs aren't giving us the full answer at these depths that are crucial for this problem. The ohmic heating problem is a very enticing mechanism that we've also heard about. It sort of has the potential of, again, driving currents that dissipate deep into the planet. The problem is that these magnetic fields also damp the winds that are necessary to drive the currents. And there's been several recent work, including work that was done at a previous ASIMO workshop here by a student and advisor, not here, I guess this is the one in Beijing, showing that this ohmic dissipation mechanism might not work in detail. And so then I just want to mention this one idea that another aspect of winds that's slightly different from the dissipation of energy is that winds produce a mixing. And one consequence of mixing in a stably stratified atmosphere is that it drives heat downwards into the interior. So this is this is an idea that's sort of fairly hard to avoid. When we have winds, we sort of expect that there's some amount of vertical mixing that goes along with those winds. The problem with this idea is that knowing it's similar to the problem with the winds, because this is sort of something that's not different from the winds, but it's an extra effect that goes along with the winds that are blowing on the atmosphere, that we're just uncertain about how deep these winds blow and where they dissipate. And there are also some technical issues that even though this effect is hard to avoid, it's also an effect that's hard to include in detailed evolution models, which don't include this type of heat transport. So I'm going to just explain in a more cartoon-based idea how these different sort of heat transport mechanisms work. This is my sort of plane parallel atmosphere modeled as a tea kettle. And so as we know in atmospheres, when there's a small amount of heat flow going through the atmosphere, it tends to be radiation that transports that heat flux. Whereas if there is a larger amount of heat flux that needs to be driven through your atmosphere, radiation cannot carry it, and instead thermal convection is triggered, and then that is then capable of driving a larger heat flux through the transport of heat by the convectively turbulent eddies. Okay, so that's sort of your more or less standard stellar evolution type version of the story. Hot Jupiters are very different in that there is a large amount of heat flux coming from the outside compared to a small heat flux that is escaping from the inside. So you generally get coming through the atmosphere is that the radiation that comes out is mostly just the reprocessed radiation that has already come in, right? And it's because this heating from the top is much larger that you tend to have these stably stratified layers on the, in the outer region of your atmosphere. So that's all well and good, but again, this atmosphere should not be unstable to convection, but we think there is nevertheless some mixing in these atmosphere, again, just due to these winds. And so the consequence of that, then, because the stratification is the reverse, is the consequences are exactly the opposite of convection. Instead of the eddies transporting heat outwards, this turbulence that we force in the radiative layers forces heat downward into the interior of the envelope. And so if that mixing is intense enough, it offers the possibility that the amount of heat in the interior can actually be increased over long enough times. And then eventually the planet would come into equilibrium at a new inflated state. And so the thing I want to say is this idea of the transport of heat is different and complementary from the standard idea that, the winds just dissipate and deposit heat locally. So the idea is you actually have both of these effects. You have the local deposition of heat plus the transport to deeper levels. So in the last few minutes, I want to describe the recent work with TAD on sort of independent of which of these mechanisms is operating, how much heat do you actually need to put into a hot Jupiter, and where do you need to put it? So it's a well-established issue that these two issues are coupled, that the shallower you put the heat in, the more of it you need to put in to explain the large radii. And so even though this is well known, we thought there was a need for a more systematic study of this issue. And in particular, it's known that whether the heat is, how close the heat is placed to this deep radiative convective boundary is important. But one thing to emphasize is that we talk about these deep convective layers. Even when the convective layer is at 1,000 bars, that is still basically the entire mass of the planet is still outside that zone. So even this deep heating is still very near the top of the planet. So here we're showing the results of some evolutionary models that were run with MESA for 209458 type parameters, where we took 1% of the stellar irradiation and deposited it with some width, order scale height or so, at different pressure levels in the atmosphere and allowed the planet to cool for 5 gig years, right? And so what we see here in these pressure temperature profiles is that there is a huge difference in how hot you stay. There's a huge difference in whether that heat is deposited at 10 versus 100 bars. This is the biggest, the sort of obviously the sort of critical critical level. And so just to emphasize that again, this is our full model suite here, where we're varying now. This is showing the radius of the planet after 5 gigayears versus the amount of heat that's added, sort of 10%, 1%, down to 10 to the minus 5 of the solar radiation. And you can see here that obviously the planet is more inflated depending on the more heat you add, the more inflated the planet gets. And again, we see this, this huge jump between the 10 and 100 bar levels. And then perhaps even more surprisingly, we see that the difference between depositing at 10 to the 4 bars, which is outside most of the mass of the planet, is almost completely indistinguishable in evolution to putting the heat directly at the center of the planet. And that's, that was quite surprising to us. So again, our conclusion is that we think that hot Jupiter radii can be explained by taking some fraction of the stellar heat and putting it into the interior of the planet. And the take-home point is that about 1% of the stellar radiation is enough to deposit, and it only needs to get, in most cases, to about 100 bars, which is not so bad. Thanks. The temperature is increasing with depth. Is that's not what you're asking?
That's what I'm saying.
Yeah.
Temperature profile is, it's hotter but low. So
Yeah.
if it's cooler up top, how are you actually
Yeah. So in all these models, we are just suppressing cooling, actually. So, right.
About the mechanical greenhouse.
Yeah. So how that works in detail of getting the heat down, this is a huge issue. I think we're going to hear more about this from Eric later. They may have found evidence for a reinflated planet. But that's a huge problem of how you would reinflate a planet, because exactly as you say, as you're cooking, if you cook a loaf of bread or something from the outside, you never expect to make it hotter on the inside than it is on the outside. So how you would transport heat down that gradient is a big issue. Potential temperature is entropy in our language. I think those are the same things. So yeah, exactly. Yeah. It's just that this is sort of a natural level for the radiative convective boundary to be, and so that by having the heating closer to where the radiative convective boundary is, you're doing a better job of suppressing cooling. I mean, it's very complicated. I mean, the details of this get fairly complicated, and this will sort of be in the paper, because it's not just where the radiative convective boundary is obviously changing over time, and so we found that we tried various things, and we found actually we could, if we tracked and put the heating directly at where the radiative convective boundary was, that was actually the best possible thing we could do for, well, as good as anything else. Obviously putting it in the center is good as well. But so that's the key issue is getting that heat near to where it's being lost from, which is the radiative convective boundary.
Thank you, Andrew, again.
and affects basic physical properties like their radii at the tens of % level. So this certainly makes them unique among planets, I believe. And yeah, quite fascinating overall. So I'm going to describe this problem in general, including some work I'm doing with Tad here, who we've seen is quite an expert in hot Jupiters from all the talks today. So I'll start with a little background, right? And what makes cold Jupiters different from hot Jupiters is that colder Jupiters are objects that are more or less fully convective up to their photospheres. But I will try to come up with a perfectly cromulent explanation for hot Jupiter radii. So yeah, we've heard a lot of amazing detail about what we know about the atmospheres of hot Jupiters with incredibly detailed spectra and then studies with GCMs of the very detailed dynamics on their surface. But one of the things that I think makes hot Jupiter such a very interesting class of planets and of astrophysical objects in general is that their surface dynamics affects their global evolution over a gigayear timescale. The size of a hot Jupiter is the issue we're dealing with, is primarily controlled by the entropy of this inner convective zone. The other factor that's important is the mass of a solid core, or the heavy element composition. Now, if you're trying to explain how things can get so big, the best case you can do is assume that you have a small core, because the more heavy elements you add, that just makes your problem even harder. And so for the most part, that's what we're going to be doing here. And hot Jupiters, because of the intense irradiation they receive from the outside, it forces the outer layers that he just sort of redistributed from winds, and so it forces the outer layers into a temperature distribution that's more isothermal, that's incapable of driving convection, and has so there's a much thicker radiative layer surrounding these hot Jupiters. Of course, even that thickness is exaggerated a bit in this cartoon. And so one of the things to keep in mind is that at least in the standard cooling models, the size. So one of the basic issues that's well known is that the effect of this radiative layer is sort of like a blanket that helps to prevent the hot Jupiter from cooling over time and helps to keep it large. And so that's one of the key issues then, is how can you make this radiative zone thicker, or how can you keep it thick over time? So again, the issue here is, why are hot Jupiters so large? And so what I need to explain is, what do we mean by them being too big? Like, what is our expectation, and what